So when you have symmetric distributions, and we are going to try to have symmetric distributions whenever possible. We'll talk about that a little bit later, what to do if it's not symmetric. But a lot of the analysis that we do assumes a symmetric distribution. When we do, we will typically find the mean. You already know how to find the mean. It's the average. So I get to tell my really bad joke. Some people say I'm average. I say that they're mean. Yeah, that was pretty bad. All right. So here's the formula. This is y bar. Anytime you see something with a bar over it like that, this is not geometry class, so it's not a segment. This is the mean. It's the sum of all the y's divided by n. This is the Greek capital letter sigma. And it's used in math. Anytime you want to add things together, they use this. Did you guys who took pre-cal last year, did you do some of that with like sequences and series? I've got some head bobs there. Okay. So, and n stands for the number of data values. N is always going to be the number of something. In this case, always the number of data values. So if you had 3 tests, you would add those 3 test grades together, divide by 3. That would give you the average on those 3 tests. So if the data is not symmetric, we'll tend to want to use the median. If the data is symmetric, we're going to prefer to use the mean. We'll go into it in a little while, but one of the things is that if you have a mean, the mean can be very affected by outliers, which is in non-symmetric data. So we prefer the median in those cases. But if it's symmetric, we're going to prefer to use the mean rather than the median. Okay? So, so if we had an outlier like the mean age of the people in the room, we did this in 7th grade, and it works today because you have a sub in the room who is going to pull the mean age up. But it wouldn't have much effect on the median age of the people in the room. So we say there's several different words you can use. I usually say sensitive. The median is sensitive to values that are extraordinarily large or small. Oh, sorry. Hang on a second. The mean is sensitive. The median is resistant. Okay, so just remember, if the data are symmetric, we prefer the mean. If the data is skewed or includes outliers, we're better off with the median. That's what you need to know. And I think we actually talked about that a little bit in pre-algebra. All right, and when we're using the median, we are going to use a better measure of the spread than the interquartile range called the standard deviation. Which takes into account for far, that should be how far each value in the data is from the mean. So if we have symmetric data and we just added up the deviations, which is the difference between a data point and the mean, if it was perfectly symmetrical, the positives and the negatives would add out to 0, or pretty close to that. There is a thing, and I don't know a ton about it. I asked some about it this summer because I was like, well, what if you just took the absolute value of all those? And there is a thing for that. It just doesn't get used very much. I don't remember what the name is now, but it's not used very much in statistics. Instead, what they do is they square the differences. And then they add up their deviations and find their average, almost. We call this result the variance. So for every point in my data set, I'm going to take that point minus the mean, square it, and then add all those together. And I'm going to divide by n minus 1. Now, the problem with using this as a measure of spread is that our units now are squared on top. And you're like, I don't really want that. So what we do is we take the square root of s squared, and the result, s, is the standard deviation. Excuse me. Did I scare Kelly? Did your eardrums meet each other in the middle of your brain? Sorry. All right, so larger standard deviations means the data is more spread out, while smaller standard deviations means that the data are more tightly packed. And when we say spread out, it's not just spread like in a huge range, but also spread out from the mean. So just as an example, let's say that you don't need to draw this, just something that looks kind of like this. As compared to something that looks like this. This second one would have a larger standard deviation because you've got more points that are away from the mean that are large or a good way away from the mean, as opposed to these, you don't have as many that are far away from the mean. Does that make sense? So on these, the range of these two is about the same, but this one is, the standard deviations are different, which is one of the reasons why we prefer a standard deviation when we can get it over just a range or just an interquartile range. All right, so if you're asked to talk about quantitative data, here are the things you should do. Start by making a picture to help you discuss the shape of the data. In most cases, the best picture for this is a histogram. If the shape is skewed or has outliers, let's add that. report the median and the interquartile range. Those two always go together. You will never talk about the median and the standard deviation together. It's always median and interquartile range and mean and standard deviation. If the shape is symmetric, we're going to report the mean and the standard deviation, and sometimes you'll also report the median and the interquartile range. For unimodal symmetric data, the interquartile range is usually a little bit bigger than the standard deviation. And then, so this is the shape. These are some numbers that go with. Then we can also talk about, so we talk about the shape, the center, and the spread, and then also be sure to discuss any unusual features. So if there are multiple modes, figure out why. Why would that happen? If you have, maybe you have two separate groups that don't really belong together. If there's any clear outliers, point them out. If for some reason you're reporting the mean and the standard deviation, you should calculate them both with the outliers present and without. Sometimes the differences are revealing. Sometimes if you toss that, you're like, oh, I have a thing that makes much more sense now, which leads you to believe that maybe that outlier really is a mistake and not simply just, a point that's a long way away from the rest of the data. Okay? All right. I think that's the end of this notes, isn't it? Yep. All right. Let me stop.